Excuse me, do you have a moment to talk about the Lambda Calculus? It's a way of thinking that's all about functions. You may be familiar with mathematical functions. You give it a value, it does something with it, and returns some resulting value. Or maybe you've encountered functions in programming. For example, in CoffeeScript, the same function may look like this. In programming, of course, you can make functions do lots of other things, too. It doesn't have to be about math or numbers. By the way, this is pencil code. You can play around with it yourself at pencilcode.net. I'll also link to this code in the description. Anyway, some programming languages also have a thing called first-class functions, where functions can also act as things or values. So, in this case, click is a function which takes in one thing, and that thing has to be another function for what to do whenever the user clicks somewhere on the screen. So every time I click, the click function looks up the thing it's supposed to do with the click, which is the makeBlob function, and then it does that. The reason they're called first-class functions is because the functions are first-class citizens, alongside other values like numbers or turtles or bits of text. Well, Lambda Calculus takes this idea to an extreme. What if functions were the only kind of citizen? All values are functions. Functions are the only type of thing there is. Everything is functions, functions all the way down. And the functions more or less only do one thing. They take in values, consume them, and plug them in inside the function. And of course, those plugged in values are themselves functions, because that's the only thing they can be. So they also want to consume values and plug them in, and so on until there's nothing left to consume. At this point, you might be asking, why? How? What? These are all great questions. According to this book, the power of the theory comes from the fact that computations, both terminating and infinite, can be expressed by lambda terms at a comfortable level of abstraction. Curiously, they've put comfortable in quotes. But the most important part here is that computations can be expressed by lambda terms. As in, all of the computations. Anything you can compute on a computer, you can theoretically do with lambda calculus, just using the one operation of taking in parameters and applying them. It might look really weird and take a really long time, but you can do it. Using the technical term, lambda calculus is Turing complete. So that's cool, but perhaps that doesn't actually explain anything at all. Let's look at some examples. Here's the simplest possible function, the identity function, expressed in lambda calculus. It takes in some value, call it x, and returns that same value. This part is the abstraction which binds whatever value we take in to the variable x in the expression, which is the rest of the function. This is how we apply the function to some value, which is actually some function, remember, because everything is functions. Or, suppose that we want to represent our original example, 2x in lambda calculus. No, this isn't allowed. What is this 2? What is this star? These are not things that exist in lambda calculus. All values are functions, and the only operation is taking in values to apply the function to them. This is the kind of thing I found confusing in most other explanations of lambda calculus. They try to simplify things by adding in other operations that aren't allowed. But that obscures the very point of lambda calculus. So it just ends up looking like a really weird but useless notation for functions. This is what 2x would actually look like, but let's not get ahead of ourselves. Okay, so what else is even allowed other than just the identity? Well, we can use the bound variable more than once. So, for example, here, the output is some function applied to itself, since applying values is the only operation, so maybe some function is the identity function. Then we still end up with some function as the result. We can also use other variables. We aren't obligated to bind all the variables we use. So here, y is a free variable. We can bind more than one variable. Technically, these are two functions. This is a function which binds x and then returns another function which binds y and does the stuff that it's supposed to do to both of them. This idea is called currying. In practice, you can more or less think of it as one function with two parameters. There are things you can do with curried functions that you can't do with multi-parameter functions, like only partially applying the values and leaving the rest for something else down the line to resolve, but let's not worry about that for now. We're not obligated to use all the variables we bound, so this is also a totally valid thing. It takes in A, takes in B, ignores B, and returns A. And now we're finally getting somewhere useful. So we have this function that takes in two values and returns the first one. Suppose we also made the function which takes in two values and returns the second one. And suppose we called one of them true and the other one false. It kinda makes sense. They're opposites of each other. They do the opposite thing. Out of two options, A and B, they each pick the opposite one. Now we have Booleans. If we can define functions that act as Boolean operators and return the right thing, we can make and evaluate any Boolean expression we like. And of course we can define such functions, otherwise I wouldn't be telling you about it. For example, this is not. So, if we try to evaluate not true, the true gets consumed and takes the place of A. Now we just have three Booleans, which looks pretty weird, until we remember that they're really functions. In particular, we can interpret that first true as taking the other two Booleans in as parameters and returning the first one. And the result is false. You might be wondering at this point, like I was, why we're allowed to give function names and then use those names in the lambda expressions. Didn't I say that there was only one thing we were allowed to do in Lambda Calculus? Isn't this a second thing we are doing? Well, basically these functions are what in programming we call syntactic sugar. They don't affect the functionality of Lambda Calculus in any way, they just make it a bit more convenient to use for us humans. We could, in principle, completely avoid them and just deal with expressions like this. Lambda Calculus doesn't know or care that this function is called true and the resulting thing is false and this thing is not. If you're now wondering about recursion, no, recursion is not allowed in these definitions. There can't be dependency loops. We have to be able to completely resolve all the names before starting on the Lambda Calculus part. You have to do other very clever tricks to actually achieve recursion in Lambda Calculus. And maybe someday I'll make another video about it. If you weren't wondering about any of that, good! Let's move on. We can also try not false, and a very similar thing happens. False takes the place of A. Then we remember that false is really a function, which takes in two things and returns the second one, and that evaluates to true. So it works! If you pass in true or false, it returns the opposite. Technically, nobody's stopping you from passing in something else, but garbage in, garbage out. But why does it work? Because it's set up so that the passed-in Boolean, which takes the place of A, gets used as a function to choose the right answer. So the key to making this kind of Boolean operator work is making sure that whatever is passed in, the three resulting Booleans in the body get evaluated the way we want. So knowing that, how could we build AND? Well, first of all, we know that it needs to take in two things to AND together. And it needs to do something with them. Modeling this off of not, we can assume that there should be three things in the body. The first one will use the other two as parameters. Again, going off of what we had in not, we can try to put the first parameter as the very first thing. That way, whatever it is, it gets used as a function. We know that if the first thing is false, we don't need to know what the second thing is, because this is AND. False and anything is false. If A is false, it will choose the second option. So we can set that one to false. Finally, if A is true, then we can just return whatever the second parameter is. Because true and false is false, and true is true. And it works. Or is left as an exercise for the viewer. I'm afraid it'll probably have to be a paper and pencil exercise. The visualizer I've been using is an interactive web-based thingy, but I haven't made a proper interface for inputting expressions. I've been doing it by editing them in the code directly, using this janky ad hoc expression format. If and when I get an interface together, I'll add it to the description. Meanwhile, small non-destructive pull requests are welcome.